Hi, welcome back to another video about LTSpice. In this video, we will discussing the halfway rectifier. I will find a appropriate pointer. So halfway rectifier. First, I would like to introduce the circuit, which is very popular in the power application. So this is the circuit of the halfway rectifier. It consists of a voltage, a diode, capacitor, and this is like the load, representing by the R1 resistor with 1 ohm, and our capacitor is 100 millifarad. The diode is an ideal diode, and this is the information of our sine wave. And as you can see, when we have this kind of circuit, we can have, this is the signals representing the halfway rectifier. So there are two signals in this graph. The first one is the sine wave, which is the input, the blue dash graph, representing our input sine wave, and the red signal representing the rectified signal at the output. The red one is the voltage we measure at the output here, and the input signal is the dash blue line, the sine wave. The normal question that we could have related to this kind of circuit is, for example, we have to calculate or estimate the ripple. So as we could look at this graph, the ripple is the value of this voltage. So as you could see, there's a transient of voltage here. This is the ripple. If we are given with the input signal is a sine wave, with the peak voltage is 10 volt peak, so the peak is 10 volt each, and the frequency of the signal is 50 Hz. We also given the capacitor is 100 millifarad, and the current going through the R1 going through the load is approximately constant 10 ampere. It means the current going through this load is approximately constant with 10 ampere. So if the load is 1 ohm, the capacitor is 100 millifarad, the diode is ideal, and the signal is given as here, then the current going through this load is constant 10 ampere. And how could we calculate that kind of ripple? First, let's look at the signal, the rectified signal again at the output. By the way, so I just want to have an addition about why this circuit is called halfway rectifier. Because as you could see, when we have the AC input, the output is the red signal. If the ripple here is very small, the signal can be considered as DC, because the AC is rectified to be the DC signal. That's why we give the circuit name as rectifier. And why is it halfway? As you could see, in one period, there will be two half period. This is the first half, and this is the second half. And when you look at the rectifier signal, there will be two stages. The first stage is the charging state, when the diodes conduct, and then the current will go through here and charge the capacitance until the voltage on the capacitance is equal to the input voltage. As you could see, this is charging state. It got charged, and then when the voltage on the capacitor equal to the peak value of the input signal, the charging state stopped and the diode stopped conducting. Then the circuit switched to another state, which is the discharging state. This is the discharging state. When the diode stopped conducting, this is open. The circuit contains only the capacitor and the load. At that time, the capacitor will provide the current through the load. That's why the voltage on the capacitance will drop until here. At this point, the diode starts to conduct again, and the capacitor started to be in the charging process where the voltage started to be charged until it's reached the peak value at the input, and the whole process repeats. So, in order to solve this problem, to calculate the ripple, our main focus should be the capacitor, how the capacitor works. This is a very popular formula of the capacitor, where we have the voltage on the capacitor times the capacitance equal to the charge on the capacitor. If we differentiate both sides of this equation with term, so this is the first sign and we differentiate with term, and the second sign also differentiates with term, we can obtain the second equation. And in this second equation, let's have a little bit of explanation. As the definition of a current, the current is like the charge going through area per unit time. So this is like the charge per unit time. As a result, it is preferred or interpreted as the current going through the capacitance. With some math transformation, we finally obtain the very important equation for this question, which is here. We have the changing voltage on the capacitor equal to the reverse of the capacitance times the current going through the capacitance. And in this case, we assume that the current going through the capacitor is constant, so we can simply just write it here as a current without any complicated formulation, because we assume that the current going through the capacitor is constant. And then we times with the time where it's necessary to accumulate such a voltage on the capacitor. And here, so let's say if we look at the signal here, the rectifier signal here again, the value of the ripple is here. So the value of the ripple can be calculated in either process. We can calculate the ripple in the charging process, or we can calculate the ripple in the discharging process. Either process will give the same value of the ripple. This is the value of our ripple. Because we are given with the current going through the load, the current going through the load is considered when we are in the discharging process. We are in this process, then the current going through the load is 10 ampere, and that current is provided by the capacitor, only the capacitor. That's why the current going through the load in the discharging process, 10 ampere, can be considered as the current going through the capacitor. So let's replace the value of those parameter capacitance, current going through the capacitor, and the time needed. So the capacitance here is 100 millifarad. The current going through the capacitor is 10 ampere, because we are considering to calculate the ripple in the discharging state instead of the charging state. One more time, as we are provided the current going through the load, but we are not provided the current going through the capacitor in the charging process, so we don't care about what happened in the charging process, just care about what happens in the discharging process in order to estimate the ripple value and for the time that we need. So how could we know what is the time that we need for the discharging process? As you could see, the discharging process starts at the peak of the signal and it goes until here. We can assume that because at this point it's very close to the next peak of the next period. So we can, from here to here, we can approximate the time that we need is the whole period. And because the input signal has the frequency is 50 Hz, so the whole period will be 1 over the frequency of the input signal, which is 1 over 50. We have the result equal to 2 volt. So our ripple value is 2 volt. Let's check the value in LTSpice simulation. This is the LTSpice simulation. If you don't know how to draw the circuit, like how to simulate the diode and other stuff in this circuit, please refer to my videos. I have the videos about everything. So just refer to that. I also put the related videos in the comment section. Please check it out. Now let's do the simulation. Let's simulate. I'm doing the time analysis of the circuit. Let's look at our input signal, which is the sine wave. Perfect. And the peak is 10 volt. Correct. We need a sine wave with the frequency 50 Hz. So if we look at here until here, is 1 period equals to 20 millisecond, corresponds to 50 Hz. Correct. Now let's check the output. So the flow line is the output. Here we obtain. Here I put the calculation again in order to check with our simulation. Let's check it out. Put 2 cursors on the output. So this is the first cursor. Let's check the ripple in the charging process. Because the ripple, either we consider in the charging process or discharging process, will be equal. So this is the start of the charging process, and this is the peak position is the end of charging process. We look at the difference between 2 cursors in the vertical direction, which is the value of our ripple, equal to 1.6 volt. So that's the charging process. Let's look at the discharging process. So the discharging process starts at the peak and then it ends here. We have also 1.6 volt, and both process gives out almost like the same value with our estimate 2 volt. So our estimation can be considered correctly. And let's see the current going through our load. Add plot and look at here. And then I will measure. Okay, so this is the current going through our load resistor, which is 10 ampere. But actually it is minus 10 ampere. Why? As you could see, this is the direction of our current, which has minus 10 ampere. So the positive 10 ampere means it going this way. This way is the positive of the current. This way is the positive 10 ampere current, and which is almost correct. As you could see, if we say the ripple are negligible, so the current going through our load can be considered as constant 10 ampere. And this is the end of the halfway rectifier. I will just briefly saying some notice when we doing the simulation of the rectifier, the halfway rectifier, in order to obtain such a nice graph. I put some notice here. In the notice, we can say with the given capacitance, we can calculate the impedance magnitude of the reactance of our capacitor, almost like 0.03 ohm. So if we gonna choose our load with the resistance very big compared to our reactance of the capacitance, then in the charging state, the current going through our capacitance will be very big, because the current will choose which component has smaller resistance, smaller reactance, and if the load has the resistance much bigger than 0.03, 1 is comparable to 0.03. That's why we can see the ripple. But if the resistance here is much bigger than the reactance on the capacitance, then the current going through the capacitor in the charging process will be very big. And when we consider again the important formula related to our capacitor, if the current going through the capacitor is very big, the capacitance will reach the peak value very quickly, and when it reaches the peak value so quickly in the charging process, the ripple won't be visible. And I will demonstrate that in this simulation with the step command. Firstly, I need to change this value into a parameter. If you want to understand what does it mean parameter in LTSpice, please also refer to my video. Let's put step command, and my parameter name is R. I will use list. The first value is our 1 ohm. Let's say we have another 1 kilo ohm, which is our second case, which much bigger than 0.03 ohm reactance of the capacitor. In that case, the current going through our capacitor will be very big. As a result, the ripple won't be visible in this case. Let's do the simulation and we can see the result very quickly. So, okay, we don't know which is the graph corresponding to 1 ohm and which corresponds to 1 kilo ohm. Let's choose 1 ohm. So in the 1 ohm, our ripple is visible. Let's see in the case of 1 kilo ohm. 1 kilo ohm, the ripple is nowhere to be seen. It cannot be seen. It doesn't mean that it doesn't exist. It exists, but it's not visible to our eyes. Let's check the current going through our capacitor. In the case of, let's select the step, choose 1 ohm. So in 1 ohm, we have around, like, let's say 150 ampere in the charging process. So you could see this is the charging process. We have the current around like 150 ampere. Let's view the other case. In this case, the current is like minus 30 ampere, and there's no ripple anymore because it's way too fast. So I hope that the videos is useful for the halfway rectifier theory. If you find that the video is helpful, please give me a like, subscribe, or comment. If you find out something wrong, or if you want to give me some opinion, I'm happy to hear all of the opinions from you. And see you in another video about maybe full wave rectifier. Goodbye.